In this tutorial, I will explain climate models ranking with data science techniques. Climate change is one of the most pressing challenges of our time, and accurate climate prediction are crucial for policymakers, researchers, and environmentalists. But with multiple global climate models available, how do we determine which one are the most reliable? In this tutorial, I will use machine learning and statistical techniques to rank different climate models, ultimately selecting the top 3 for multi-model ensemble computation, a method that improves climate projection by combining the strength of multiple models. Our journey begins with data pre-processing. Here you can see, let's visit the code. Here you can see I have imported these libraries, and with this piece of code I have imported the data from Excel, which contains the global climate model and observed data. So in the next piece of code I have dropped 2 columns, that is year and month, and then in the third, fourth step I have, as we have some missing data in the data, so I have replaced this missing data. So basically our journey begins with data processing. We first load climate model data from an Excel file, ensuring that missing values are handled effectively using mean imputation. Additionally, we remove irrelevant columns such as year and month, as I have already mentioned, as they do not contribute to the ranking processes. By focusing purely on the climate model and observed climate data, we prepare a clean data setup for further analysis. So in the next step, we have defined our target and input variable. So here observed data is our target variable, while the climate model are our input variable. In the next step, that is basically principal component analysis, which is a dimension reduction technique. So this piece of code is basically used for the principal component analysis from this to this. So basically this technique is a dimension reduction method that helps us to identify dominant climate patterns in the dataset. By transforming the data into principal component, we can better understand the underlying variability in climate models. A scree plot usually represents the explained variance of each component, allowing us to determine the number of significant components that ensure the most meaningful pattern. Additionally, an interactive variance chart gives us further insight into which principal component hold the most information. In water quality, we usually take eigenvalue 1. All those principal components whose eigenvalue are greater than 1, we usually use that for the identification of pollution sources, but here we will restrict ourselves to the first principal component. So now move to the next step, next part of the code, which is recursive feature elimination technique with random forest. So here you can see this piece of code is for recursive feature elimination technique. So here you can see with these techniques, here we implement recursive feature elimination with a random forest regressor. RFE is a feature selection technique that systematically removes less important variable, refining the ranking of climate model based on their predictive power. By using random forest, an ensemble learning method that handles complex interaction between features, we ensure that the ranking is both reliable and robust. The results are visualized using a heat map inspired interactive bar chart, where models with higher importance stand out more prominently. So in the next step, we carried out SHaP analysis. This piece of code is for the SHaP analysis from here to here. And what is SHaP analysis? Basically, SHaP analysis explain a powerful SHaP analysis is a powerful model interpretability technique. SHaP values help us to understand the impact of each climate model on the prediction. Unlike traditional feature importance method, SHAP provides local interpretability, meaning it explains how each model affects individual prediction. We generate a SHAP summary plot to observe overall feature contribution, while a dependent plot highlights relationship between key variables. Additionally, an interactive SHAP feature importance chart make it easy to see which model have the greatest influence on climate variability. And this, the last piece of code is basically, this is for the ranking of the models. So after combining the insight from principal component analysis, recursive feature elimination, and SHAP, we arrived at our final ranking. The top 3 GCMs selected based on their combined importance across these techniques will be used for multi-model and simple computation. MME is an advanced approach that improves climate prediction by averaging multiple model output, reducing biases, and increasing overall accuracy. By leveraging the base model, we ensure that climate predictions are more reliable, interpretable, and data-driven. Our data-driven ranking approach provides a systematic way to evaluate climate model, helping researchers make informed decisions. What are your thoughts on this method? So you can drop it in the comment. So now run the model. When you run the model, so here you can see we will get the results. So basically we will start from the scree plot. So here you can see this is a scree plot where explained variance is plotted against each principal component. So here we will select the first principal component for the GCM ranking. Here this is again the same scree plot but with different colors. So here you again you can see that it explains 36% of variance out of all these principal 31 principal components. So this is the most important components, and so you can see over here that the loading of these principal component is explained in this table. Here you can see this is PC1. So this is basically the coefficient of different climate models. So based on these we will select the top 3 models for multi-model ensemble computation. So now again move to the next section, that is RFE ranking. So this is the second technique. Here you can see that it has ranked all the climate model. So all the model which rank first will, the top 3 model which rank first will be selected for the multi-model ensemble computation. So once again here you can see this is the third technique, SHAP. So here you can see we will select these 3 climate models for the multi-model ensemble computation, and again it is explained by this loading. So we will select all those components which have the higher ranks, and this is the principal components, those principal components which are most effective. So this is ECR or CNRM, these 2 are most effective, and this is at the end this is the ranking based on RFE and feature important score. So once we select the top 3 models from each technique, then we will go for the multi-model ensemble computation, which is the part of the next video. So let's know in the comments below, and don't forget to like, share and subscribe my channel for more content on climate science, machine learning and big data analytics.